All right.
Welcome everybody back from lunch. So our first afternoon speaker will be Moses Charikar, visiting us from Stanford to talk about sketching for kernel density estimation.
Okay, thanks everyone for coming. I'm going to try doing a whiteboard talk on this one. So let's see how this goes. So the problem I want to talk about is the kernel evaluation problem. So here's the problem. You're given a data set of points. Let's say there are n of them. Three-dimensional. What we have to do is we got to pre-process these points so as to be able to answer queries. And what are the queries that we want to answer? The queries are points in this space. And given a query, we want to compute the sum over the data set. The sum of this so-called kernel function over the entire data set. Okay, so there's some function k pq. Think of this as a function that drops off as you go further and further away from p. So each point in the data set has some sort of force field. Drops off. Let's say it's symmetric, it's radial, it depends only on the distance, it's monotone. And what we want to know is, at the query q, what's the net force from the entire data set? Okay, so that's what we want to. So we want to evaluate this function. So let's put some conditions on this kind of thing. We'll say that this is a positive definite radial kernel. So radial just means the value in any direction is the same. It just depends on how far out you went. Okay, so that's what radial means. What does positive definite mean? Well, positive definite just means that if you take any m points, x1 up to xn, and you form a matrix with all of the pairwise kernel values, a, xi, xj, then this matrix is positive definite. So for any set of points, if you plug in this kernel value for all pairs in the ijth entry, this matrix is going to be positive definite. That's the nice consequences of having this. All right, so far I've just defined a problem. I'll tell you very briefly why we care about it, but let me give you some examples of kernels that people think about. One kernel that we will talk about is the Cauchy kernel. More generally, there is the so-called rational quadratic. And that's just a kernel whose expression is given by 1 over 1 plus the distance between p and q raised to the power of. Okay. So all of these radial kernels, they only depend, the value of kpq just depends on the distance between p and q. This is the particular dependence here. Another kernel that we will talk about is the so-called student T kernel. And this expression is just 1 over 1 plus raised to power. Okay. So again, it just depends on the distance between P and Q. All right. So why do people care about these kind of kernel problems? Turns out that these things have many applications in machine learning and statistics and data analysis. I'm actually not going to get into the specific applications. I'll tell you one, what got me interested in these problems in the first place. So I was chatting with a colleague of mine shortly after arriving at Stanford around 2015, Peter Bayless. He's in databases. He uses sketching methods and all the things he does. And he was thinking about how do you find outliers in data. And he had a particular method. His method involved basically just doing this kernel evaluation. Given a data set, run this procedure for a new point, treat this new point as a query. And if this value turns out to be high, well, it's kind of like it's near the typical data set point. If the value turns out to be low, then it's far away from much of the data set. So that was the test that he was using to determine whether or not there's an outlier. It just got me thinking about, how you would do this efficiently. How could you do this without actually making a linear pass of the entire data set? Because that's the obvious thing to do, right? If you wanted to evaluate this quantity, the obvious thing to do is to just make a pass of the data set at some of these n quantities. Can you avoid that? Okay. Now, by the way, in non-parametric statistics, this kind of kernel evaluation procedure is pretty standard. The idea is that if you're given samples from a distribution and you don't want to make any assumptions about this distribution, then one way to extend this empirical distribution to the entire space is to use a function like this. So essentially, you smear the data, smear each point out over the entire space. Okay, so, and my initial thought was, maybe some methods like locality sensitive hashing, all of the nearest neighbor literature could be leveraged to solve this problem. We'll come back to that thought a little bit later. Okay, so that's how I got introduced to these problems. But these problems have been around for a while. Okay, so I mentioned nearest neighbor, and whenever we solve nearest neighbor, we don't really solve it exactly anymore. We sort of approximate it. And same with all these kernel evaluation problems. We're going to be happy with getting some kind of approximate value. And the approximate value that we want is something that's between 1 plus minus epsilon. So we're happy with any estimate, which is, let me write it like this. Okay, so, but it works. Okay, so we're happy with anything which is within 1 plus minus epsilon of the actual value. And the question is, can we do this efficiently? How much space do we need for this data structure? We're going to pre-process the data, and how quickly can we answer the queries? Okay, so this is the question. All right, so even before computer scientists or theoreticians started thinking about this problem had been around for a while. And in the numerical analysis literature, this is something which is the domain of what's called the fast multipole method. So this is sort of a bread and butter algorithm for people who do standard computation, numerical analysis, exactly for the kinds of computations where, let's say you have n bodies, they each exerting forces on each other. You'd like to figure out, what's the net force on each body. In fact, you want to do this multiple times because maybe you want to simulate the system, how the system evolve over time, and so on and so forth. So you're really very interested in doing this very, very efficiently. So the fast multipole method is a classic method that's been developed for this. And typically, the settings that people are concerned in practice in these settings are three-dimensional settings, right? N bodies, or two-dimensional settings. In fact, if you take these methods and try to extrapolate them to higher dimensions, the dependence on dimension is pretty bad. It's exponential in the dimension. So roughly speaking, the space behaves like n to the power of log n over epsilon to the power of d. Okay. And the query complexity also behaves like log to the power of d. Okay. And very roughly speaking, this kind of exponential in D dependence is because these methods rely on a deterministic space partitioning technique. So they take space, they chop it up in some way, and then they do things like, well, if your query is here, and look at all this data that's sitting in this square. Turns out that there are good ways to approximate the net effect of all of these points on this grid like that. So they chop space up at different levels of resolution and so on and so forth, and they do some kind of analysis like this, which leads to very, very efficient algorithms. The way in which these methods are usually quoted in this literature are their linear time. But in fact, there is this exponential dependence on D because they're not really concerned with, they were never concerned with high dimensional setting. With high dimensional setting makes sense when we start thinking about machine learning and data analysis, where we really have high dimensional points. So, all right. Okay, let me, that's all I'll say about these methods. So, as I mentioned, the genesis of at least my work in this area was sort of this chance conversation with a colleague, which got me thinking that perhaps sampling-based methods could be used for this. And so now there's actually a bunch of work on this. And let me just bundle it into one. So there was an initial paper that I wrote with a student of mine, Paris Similakis. I actually spoke about it here, I think, a few years ago. So there's been a few papers after that, and I'll summarize what the net, what we know about this. So I'm going to write a bunch of acronyms here, and maybe I'll mention some of the authors. So this was work with this student Paris Similakis. Later, we teamed up with Piotr Indyk and Arthur's backers to do a little improvement on this. We introduced the notion of smooth kernels, which I'll actually get to in a second. There's also work by Backers, Indyk, and Wagner. And then other work by with Michael Kapralov, Navid Nouri, and Paris, which was in. Okay. The net result of the high-level idea of all of these methods is that locality-sensitive hashing data structures, which were originally designed for nearest neighbor search, could also be used as data structures for solving this problem. And why is that? Well, you could think of locality-sensitive hashing data structures as giving you a way to sample points. Sample points in a distance-dependent way. You're more likely to sample points that are nearby the query than points that are further away. And this kind of biased sampling is in some sense an important sampling. So if you wanted to estimate the sum, right, you could just independently sample queries and figure out how many samples do you need in order to get a good estimate. A cleverer way to do this would be to say, well, maybe some terms in the sum are pretty high and some terms are pretty low. I really should be sampling the higher terms with higher probability. Right? If I could do that, then I can reduce the variance of this estimator, and maybe I get some advantage. That's exactly what locality-sensitive hashing allows us to do. It allows us to estimate this quantity by giving a higher probability to exactly the terms in the data set P that have a higher contribution. Now, all this has to be analyzed, but that's basically the gist of the idea. And very roughly speaking, in the very first paper that we had on this, we showed that you could do. Okay, so first of all, let me tell you what the benchmark is. So if you're going to do random sampling, first you should ask, what happens if you just random sample a data set? and try to estimate that quantity. Okay? So the benchmark for this is just uniform tau. And if you did that, then the number of queries that you need is the number of samples that you need is order of d divided by epsilon squared mu. Okay. All right. So this is the amount of time that you would take. And what we showed initially, and this has been improved since, was that by using locality sensitive hashing ideas, this can be improved to epsilon square root of mu. I didn't actually explain what mu is, so let me explain what mu is. All of these results are going to be parameterized by mu. So mu is just the value. So divided by. Okay. I'm going to mention. Sorry? The correct value divided by n. And let me just mention one more thing. I'm going to make an assumption here throughout that all of my kernel values are, let's say, between 0 and 1. Okay, so it's all normalized. Everything's between 0 and 1. The maximum value is n. Mu is just telling you what fraction of this maximum value you have.
Is the d value the sum or the average?
So I define this to be the sum, but here I'm actually, sorry, this is too low. But you know this stuff. Anyway. Okay, so
Hey, could I ask questions? So the fast multiple method, do they have dependence hidden also to the correct value, to the maximum? That mu appears also somewhere in this.
yeah. So actually, the fast multiple methods, as far as I remember, and actually it's a good thing that I have my co-authors in the audience because I'm going to lean on them to answer all the difficult questions. These produce additive errors, as far as I know. So I'm being a little bit.
They are not 1 plus epsilon times it is.
I think so, but I'm not sure. Do you guys know?
This is additive epsilon by n. Let's say for reading a small. But really 0.12.
Okay, so let me write that down. Michael says
0.12. 0.12.
additive epsilon. Okay, and let me just put that in quotes. Sort of. Okay, so the guarantee is a little bit different. Not quite. Okay, questions about this? All right. So what was the main point of this work? The main point of this work, and this is not the last word, by the way, that we, this got improved a little bit. I won't say exactly what it was, but the main point was, if this is the benchmark, can we improve the dependence on mu? And it turns out that you can. You can actually improve the dependence on mu to square root mu in the first work, and then later we improved it to mu to the power of 1/4 or something like that. Okay. The other question you could ask is, what about the epsilon dependence? Okay. So the epsilon dependence is epsilon squared. It's quadratic in epsilon. And a natural question is that the best thing possible? Okay. So we'll come to that question because that's actually going to be the topic of much of the topic of today. All right. Okay. Any questions? Okay, let me leave this here since this is the problem definition. We're not going to need the actual kernels here, so I'm going to erase that. And you all know what approximate means, so I'll take that out. Okay. There's a particular class of kernels that I'll be talking about, so-called smooth kernels. So this class was defined in this paper by Backers and Numericals. And roughly speaking, these are kernels that decay polynomially with distance. Okay? I didn't define the Gaussian kernel, but if you think of the expression for the Gaussian, it drops off exponentially with distance. These kernels are those that drop off polynomially with distance. And it turns out that for these smooth kernels, you can actually get a polylog dependence. Okay. So here, these methods that I mentioned before get an improved dependence on mu. But in fact, if the kernel has even more structure, it has this polynomial drop-off, then you get a polylog 1 over mu dependence. The space complexity becomes roughly n polylog mu divided by epsilon squared, and the query time is roughly polylog 1. Okay. So all we did was again improve the dependence on mu. We didn't change the dependence on epsilon. Right. Now, in some sense, this dependence on epsilon, this quadratic dependence on epsilon, is inherent in any sampling-based approach. If you think about sampling, just the basic sampling approach, you'd have to analyze the variance of the estimator, use Chebyshev's inequality. That's exactly where this quadratic dependence on epsilon is coming from. Now, in numerical analysis, in cases where this 1 over epsilon squared dependence is prohibitively high, there's a certain class of methods that they call quasi Monte Carlo methods. I didn't know this term, but I have to thank my co-author, Michael Kavralov, for introducing me to this term. Actually, introducing both of us directly to this term. So what quasi-Monte Carlo methods are methods that are based on discrepancy theory. And if this sounds like a bunch of new jargon, I'll hopefully try to deconstruct and explain what this is. All right, so what's the main idea? The main idea is, instead of actually random sampling, what we're going to do is we're going to produce a random-like set of points. So we're going to produce a sample, but not by random sampling, but it will have random-like properties. In fact, it will have better than random-like properties. Okay, that's the premise. Okay, so this approach, this discrepancy-based approach, was actually applied by Phillips and Thai in a paper in 2011. Okay, and what they were trying to do was to get small core sets for this kernel evaluation problem or kernel density estimation problem. Okay, and I'll say a little bit more about how this works, but let me give you a sort of a high-level idea. Okay. The idea is, let's do the following. I said sample a bunch of points at random. Let's think of the sampling happening in phases. Let's first subsample half the points, and then after that we'll subsample further and further and further till we get down to the sample size that we want. Okay, so each of these subsamplings, each time we go down by a factor of half, we view this subsample as being obtained from a random coloring. Imagine assigning colors +1, -1 in some clever way. Okay, and now we'll analyze the properties of this coloring, and from that we'll get some guarantees on the kernel density problem. Okay, that's a very, very high level, but I'm going to get to you. I'm going to give you some more details. All right. it turns out that there's a beautiful theorem of Banashik, which promises linear discrepancy. At this point, this doesn't make any sense. So don't worry about it. There's a certain combinatorial quantity called discrepancy, and there's a beautiful theorem that actually gives us some good properties for this quantity. Using this theorem, what Phillips and Tai were able to do was they were able to get space, which is polynomial in D divided by epsilon mu, and the query time, which is polynomial in D divided by epsilon. Okay. And notice, forget about the mu dependence.
It's epsilon.
Sorry?
It is epsilon, not epsilon square.
Yes, that's the key point. The key point is that they got a 1 over epsilon dependence instead of the 1 over epsilon squared. Okay. So now there are two classes of methods. Sampling-based methods, which don't fix the epsilon problem. They give you 1 over epsilon squared dependence, but they get you better dependence on mu. And then there are these discrepancy-based approaches, which don't bother about the mu dependence, but get you better dependence on epsilon. And the main question that motivated our work was, can we get the best of both worlds? Okay. Can we get the best of both worlds for these smooth kernels, right, where we're able to get polylog 1 over mu, but with a bad dependence on epsilon. We're also able to get 1 over epsilon dependence, but with a bad dependence on mu. Okay, so is the setup clear? I'm going to raise the problem now because I think you all know it. So this is work with Michael Kapralov and Eric Weingarten, who are both in the audience. Will appear at I believe, right? Okay. So what we show roughly is that we can get polylog 1 over mu dependence with linear in epsilon, linear in 1 over epsilon. Because we can get best of both worlds with some caveats, which I'll explain in a second. Okay. All right. So first, I should tell you technically what is a smooth function. So this is what smooth function is. We don't actually need the definition, but just for completeness. So if you have a kernel, I'll say that this kernel is, there are two parameters, L, T, smooth, if it satisfies the following. Okay? If you have P1 and P2 in some query Q, the main question is, what can I say about the kernel value for P1 and Q relative to the kernel value for P2 and Q? Okay. And actually, I'm going to look at both of these quantities, this and its inverse, and ask how large can these ratios get? Okay. And for a smooth kernel, these things depend on the distances between points in the following way. So P1 minus Q divided by P2 minus Q and its inverse. So this quantity raised to the power of 2 times some proportionality constant. So if a kernel is LT smooth, then it has this kind of dependence. This is what I mean by drops off polynomials. That's the formal definition. Right. Okay, so what's the main result? The main result that we are able to show is that for such kernels that have this kind of property, we can achieve space, which is, it's a slightly ugly expression. Let me write it down. V log query time is the same thing without the n. Okay. So we can get a 1 plus epsilon approximation with this kind of parameters. Right? Okay. So what's the main point? The main point is that we got a dependence on log 1 over mu instead of mu. We got a dependence which is linear in 1 over epsilon instead of quadratic in 1 over epsilon. Okay. There are some other additional ugly factors that we got along the way. Some maybe you can eliminate, some seem harder. So one factor that we have is this aspect ratio phi, which I did not define. So phi is just the aspect ratio ratio of maximum distance to minimum distance. Okay. All right. How am I doing on time? Okay. So let me give you a flavor of how these techniques work. Okay. So in order to give you a flavor, what I'm going to do is, maybe I'll do this. I'll try to give you a view of this result, okay, because it will give me a way to talk about how exactly discrepancy comes in. Okay. So okay. So what I want to do is I want to tell you why is this quantity discrepancy a useful quantity to think about if you wanted to do this kernel density estimate. Okay. All right. So I said you're going to think of sampling the data as repeatedly subsampling. And each subsampling step can be thought of as a coloring of the data into two sets, +1 and -1. So if you think about the following, think of a coloring which assigns to every point -1 and 1. And let's think of P prime as those points that get assigned color 1. Okay. What we'd like to do is the following. We want to find a coloring chi of P such that if you look at the average K, P for all the points in P, right, minus the average over just the points that are in P prime, I want the average of the entire set to be close to the average over P prime, which is about half the set. Okay. I would like for this to be less than equal to epsilon mu. Okay.
So are you requiring that P prime be emphasized?
I'm not. But P prime is going to be, if this was this is a random coloring, the expected size of P prime will be half. Okay.
Yes. You want this for any cube or for a fixed?
Yes, correct. So this is not just for this one cube, because that would be very easy to do. I want this to hold for all queries Q. Okay? So I want this quantity to be less than epsilon times mu for all queries Q. Right? If I could do this, then I'll just do this repeatedly. I'm going to then repeatedly subsample and subsample and subsample till I get down to the right size. Okay? Now, you can analyze this by using random colorings at every stage. Okay? And the kind of analysis that you would do will actually recreate the bound that you get from Chebyshev's inequality. Okay? The trouble is that there is some, if you do random sampling, it's harder to control this difference. Okay? So there's a better way to control this difference via these methods called discrepancy. So this quantity, the left-hand side, is just the sum over the points in the set where I assigned color 1 to the points in the set where assigned color -1. Okay, this is why it's called discrepancy. It's the difference between the +1s and the -1s. There's a suite of techniques that show how to achieve small discrepancies, small values. And this is exactly what you need to implement the subsampling procedure. Instead of random sampling, what you should do is you should just use low discrepancy colorings. Okay? So that's exactly what Phillips and Ty do. They combine this with low discrepancy colorings. And now,
Can I ask something about the equation? Before
Yes.
we said that all the idea is to achieve somehow to do important sampling and keep the ones that they have higher value. Can you connect that with why we need the discrepancy to be low?
so now we're not doing that at all. Okay, so that was a random sampling approach, right? Where yes, we're doing this important sampling and sampling the things with higher value with higher probability. Now I'm actually just giving you a little more insight into how the discrepancy-based methods work.
Oh, yeah.
Why discrepancy is even useful? Why does it make sense to think about discrepancy? Does that make sense? Okay, so set that intuition aside for now. We're not actually using that intuition at all. Okay. All right. So how am I doing?
It's like 3 minutes.
Okay. All right. I'm going to be very, very quick. So what do you need for this discrepancy to work? So I mentioned that there is a theorem due to Banashik. Okay, so Banashik's theorem says that this quantity, which is the discrepancy of the coloring chi on the dataset P with respect to Q, this is less than equal to order of the gamma 2 norm of this kernel matrix. Okay. Now this sounds like a bunch of jargon, but it's actually just the following. Let's take this kernel matrix K. It's positive definite. Right? This means that there is an embedding of this kernel matrix such that the kernel value for x comma y is equal to the inner product between phi x and phi. Okay. What's the gamma 2 norm of this matrix? The gamma 2 norm of this matrix is just the maximum of the phi x norms times the maximum of the phi y. Okay. Now, in order to, for Phillips and Ty, in order to get their result, what they did was they said, great, let's do this. Let's apply Banashik's theorem. Let's apply the discrepancy bounds that you get from that in here. And in order to get they needed a gamma 2 norm estimate. They said, well, this is a kernel matrix. Also, the kernel values are at most 1. So in fact, there is an embedding such that each of these are at most unit vectors. Everything is at most a unit vector. So in fact, the gamma 2 norm is bounded up above by 1. That's the main idea, right? Okay. So in just 2 minutes, let me say one main idea that was helpful for us. What we realized is that if you have a smooth kernel, and if you have a certain geometric condition, so there's two situations. One is you have a query that's sitting inside this ball here, and then the rest of the data set is outside this ball. Or you have a query which is sitting outside this ball, and the entire data set is sitting inside it. You have some sort of geometric separation condition. It's kind of similar to the kind of conditions that are used in fast multiple method. So if you have either this or this, then if you look at this kernel matrix, it turns out that you can get a much better bound on the gamma 2 norm. Okay, and how do you do that? So roughly speaking, you can write out sort of the expansion of look at the Laplace transform, write out the expansion of the kernel. That gives you a natural embedding. Okay. We tweak the embedding a little bit to make sure that these points, which have small norm, get a little bit of a boost, and these points that have larger norm actually get a boost in the negative direction. Okay, so you can adjust these embeddings so that you change the factors term by term. The product still remains the same. So this condition still holds, right? But if we went inside the dimensions, the individual dimensions, we changed those dimensions so that these things here become a little bit bigger. These things outside get a little bit smaller. And amazingly, this kind of thing can be arranged so that you get a much better bound on the gamma 2 norm. Okay? So this is the main idea. Now, of course, our data set doesn't satisfy this condition, right? It's not like this at all. So what we have to do is we have to do a randomized partitioning of the data by carving out L2 balls. Okay? And using this idea, we ensure that we're always working on portions of the data set that satisfy either this condition or this condition. Okay, I'm sort of hiding a lot of details under the carpet, but that's the main idea. Yeah.
So in this argument, like, where do you use the fact that you do have smooth kernels?
Yeah, good. So I didn't actually get into enough of the detail in order to be able to say that. But roughly speaking, when you look at the error that you get, you have to look at the ratio of the error to the value of the kernel. Okay? So you need to know how much error did you introduce and what's the value of the kernel. You want that ratio to be at most epsilon. Okay? So in that calculation, we really use the fact that we have a smooth kernel. Okay? Because what's actually happening is we're operating on the data where the data is all sitting inside a big ball and outside a tiny ball inside. There's another ball here, another ball here. What we know is that, let's say, our query is sitting in here, our data set is sitting in here. Now, when you calculate the value of the error relative to the value of the kernel, it's some function of these 4 radii. Okay? And in that calculation, the fact that the kernel is a smooth kernel comes in. It's actually useful. Okay? Thank you.
Maybe we can take a couple questions. Actually, I had a question first, which is, so I didn't understand the definition of gamma 2k. So what domains are x and y being taken from?
So I just said, yeah, I was not being very specific. So, x are these guys, y's are these guys. Okay. So they're really the same domain. We have this kernel. We write it out as the inner product. There's a gram matrix. So think of it like this. What does it mean for a kernel to be positive semi-definite?
Are the rows there just capital P? Or I guess
The
maybe
rows are just the points. Yes, yes, yes.
so why isn't this just the square of?
It's a square.
Oh, it is.
yes.
Okay.
It's a square in this case. But what we do is we treat things a little bit differently, because when we write out this thing, we're going to look at the possible queries as one dimension and the dataset points as the other dimension. Okay, and we're going to treat them differently. So it's actually relevant for us that we treat x's and y's. That makes sense?
More questions? Moses. Then let's thank him again, and Bing Wee is up next.